and welcome to Sean White's Solar and Energy Storage Podcast. This podcast is part 4 of a 4-part series on energy storage systems and the National Electrical Code with Bill Brooks and myself, Sean White. And the emphasis of this podcast is going to be about interconnections, including supply-side connections and load-side connections. Be sure to get Sean and Bill's latest book, which is the 3rd edition of PV and the NEC, and that is based on the 2023 National Electrical Code. To find out where to get different versions of the NEC, including the 2023 NEC and all kinds of different codes that are adopted by different jurisdictions, go check out the NEC tab of the website Solar, SEAN, that's solarshawn.com, where we will supply you with lots of information on all kinds of things, including supply-side connections, which is called a source connection to a service in the 2023 National Electrical Code.
Supply-side connections, otherwise sometimes called line-side taps, but the correct terminology is supply-side connection. And big change, or not a big change, just they changed the name of it or where it was. Before, in 2017 NEC, it was 705.12a, and in the 2020 NEC, 705.11. And also we have like some different rules. In 2017, you would say the sum of the overcurrent protection devices shall not exceed the rating of the service. And then in the 2020 NEC, where we can get away with a little bit more because the sum of the power source continuous current output shall not exceed the ampacity of the service conductors. And not exceeding the service, I think both of these is going to be kind of rare that people are going to have a PV system or an energy storage system that's going to be able to export that much that it's more than the service. You'd have to be doing something where you're just running full blast 24 hours a day, maybe a Bitcoin mining operation, something like that. And then it says other than those controlled by, and this is a new one in the 2020 EC, and that is 705.13, and that's called power control systems. So that means that we could control what's going on. So that's kind of neat, and maybe kind of relates to what Bill was just talking about, being able to control things.
Yeah, and so there's not a tremendous amount of difference between the 17 code, which you're currently on, and the 2020 code. Let's say you have a 100 amp service and you wanted to put a 100 amp PV system on the supply side. According to the 2017 code, the breaker rating is going to be 100 amps, which means that it's going to have a continuous output of 80 amps. All right. And so that's going to be well within the rating of the service conductors and the service equipment, because the rating of the service is 100 amps. With 2020 code, it's just a little more exact, saying that the continuous output current of the system, 80 amps, then you would look at the ampacity of the service conductors. Well, if you know anything about residential service conductors, they're permitted to have ampacity that's less than 100 amps. So 2-aught aluminum actually doesn't have a full 100 amp ampacity to it. All right, it's like 93 amps, something like that. And so we're still not going to put more than 93 amps through that. We would be permitted to go up to the ampacity of the service conductors as they're portioned in Chapter 3. Anyway, just to point that out, and then this whole idea of a power control system means that you could literally have a 200 amp PV system connected to a 100 amp service, but the power control system would limit the current going in the reverse direction by monitoring the service conductors. And so what it could do is it could feed 100 amps to the house, worst case, 100 amps to the house and 100 amps back to the grid. But in no case could it ever source more than 100 amps back to the grid. And of course the house is going to have a 100 amp breaker on it anyway, so it could never source more than 100 amps to the house anyway. So the power control system prevents the overcurrent going back through the service conductors where there is no overcurrent protection.
Conductors, they're in no case can they be sized less than a 6-gauge copper or 4-gauge aluminum. And they shall be installed in accordance with 230.30 and 43. So that's Article 230 is services. This is a little bit different, right? Because pretty much we have to bond it like a service, right? And in 2017 NEC, we had an option, but everybody kind of bonds it and grounds it like a service anyway.
In general, everything gets bonded like a service. And so if you're familiar with how services get bonded, that's the way we're doing all this stuff. And this is all 2020 code, but basically we're just trying to make it clear and add some additional words, because in Article 230, you're permitted to use much smaller than 6-gauge conductors for services, because you can have a 30 amp service to certain pumps and things like that. You could have a 60 amp service. Houses, 1 and 2 family dwellings, are not permitted to have a service any smaller than 100 amps. If it's a new service, but you have 60 amp services that are currently in existence today, and that's fully acceptable. And of course, those are going to have number 6 copper, probably, or 4 aluminum connected to them.
Overcurrent protection with supply side connections and readily accessible location outside the building or inside the building. Overcurrent protection in dwellings needs to be within 10 feet from the point of connection. And other than residential dwellings inside, it needs to be within 16.5 feet of the connection point. Or if you wanted to go further, you could just have cable limiters just to prevent short circuit currents. If there's a short circuit, it can open up the circuit at the cable limiter. And they put those within 16.5 feet. Then you can go 71 feet. I always thought, it's like reason these numbers are so odd is because they're trying to go metric. Yeah. But hey, this is America, Bill.
That's right. And again, this is the 2020 code, but it was trying to set some guidelines. So in the 2017 code, we have to put cable limiters in if our circuit goes more than 10 feet from the point of connection. If our overcurrent device is more than 10 feet from the point of connection, then we're required to put cable limiters at the point of connection. And then there's no limit on the distance. So you could go literally 1,000 feet off the cable limiter, and that would be okay. In the 2020 code, we just tried to put an upper bound on cable limiters because we know that by the time you get that far away from the equipment, there's always an opportunity to put an overcurrent device. And the cable limiter is just, as Sean just pointed out, cable limiter just handles fault current. It doesn't handle overload. Whereas an overcurrent protective device does both fault current and overload protection.
And so this is new stuff too for 2020. So bonding and grounding, they deleted some stuff. And so now we use 250-25 that refers to 250-24. And so we're going to pretty much do bond and ground it like a supply side connection, do it like a service. Before we had a different option where we could have a single point of grounding for the rest of the house and the supply side connection. And now we need 2 different single points of system grounding. So we treat it sort of like a separate service, which kind of makes sense anyway, because you're on the supply side of the main service disconnect anyway. But I think one time you were saying, Bill, that in 2023 they might change it back so you have both options. Is that?
We're seeing. We just went through the first draft. There's lots of discussion on this particular item, so we'll see where it goes.
Now we've graduated from supply side connections and we're on the load side. So it used to be 705.12a was supply side connections, and now it just says we need a dedicated overcurrent device and disconnect. And that's pretty much not really a change except the place that they put it. And what that means is why they put that there. One reason I always think is like, what if you could just plug PV into your wall? Then you could get a whole bunch of power strips and just plug PV into it and loads and all different kinds of things. And pretty soon something would start smoldering. That's why you cannot get a PV system that plugs into your wall.
At least at this point.
No. Or else they'd need to change the code pretty much, I think. Mm-hmm. You can get one on eBay.
Absolutely.
But that was all for just experimentation and demonstration of what not to do.
Amazon, you can do anything you want on.
That was when I was backfeeding that Tesla at 70 watts. And then also you got to think too is the NEC does not apply to cars and boats and things like that and trains. We're going to talk about the load side connections, the feeders, the taps, and the bus bars. And so the bus bars, that's where our 120% rule is that everybody's so familiar with. The labeling, the marking that we do for things suitable for backfeed and fastening. Feeders. Let's just kind of explain what a feeder is. And I like using the example of a feeder as being something that's going to a sub panel. So you got like a feeder breaker, the main service panel, go into a sub panel. One of the things too about a feeder, it's going to have overcurrent protection on the supply side of it. That's what a feeder is. If you are on the supply side of all overcurrent protection, it's not going to be a feeder. It's going to be like a service entrance conductor, Whenever we're doing a load side connection, we're all of a sudden putting more current on the load side. If we did a supply side connection, we're still all protected by the main breaker. But once you do a load side connection, you're adding more current on the load side of things. And so we have to figure out where that current might go. B1A, the one way to do it is you take 100 amps times 125% of inverter current, 12.5 amps times 125%, that's 1.25, is going to give us 16 amps. So 116 amps. The easiest way is to make sure that conductor can handle 116 amps. If it can, we're set. If that conductor can't handle 116 amps, we can put a 100 amp breaker. And so we got this 100 amp breaker and it's protecting this from having too much current. And so a lot of people want to put that 100 amp breaker in the sub panel, or maybe there's already one there. So if we put that 100 amp breaker there, then it kind of works, but the way that we like to look at it is if further than 25 feet from this connection point, we're going to get into the tap rules in a little bit, then you probably can't get away with that.
This is what a lot of people call the Hawaiian tie-in. This was kind of something we made popular in Hawaii years ago because 100 amps main breaker services. So you have a meter main with a meter socket and 100 amp main breaker going to a sub panel inside the house. How do you connect into that? Well, the best way to do that is this way, where you connect into that feeder that goes into the house, and often that sub panel doesn't need to have a sub panel breaker on it. So if it doesn't have a sub panel breaker on it, then installing another 100 amp overcurrent protective device allows us to go all the way up to 100 amps with that inverter overcurrent protection. So that would be an 80 amp PV system, a very large PV system. And because it rhymes, it was called the Hawaiian tie-in. There you go.
The tap rules, some people find the tap rules a little counterintuitive sometimes. What the tap rules are for, let's just even talk about the regular tap rules without solar. I could connect something to a feeder, like a load or whatever, that has a 15 amp conductor if it's within 10 feet. And if I short circuited that 15 amp conductor, since it was so short, it still would open up that breaker just because there's not a lot of resistance in that wire because it's so short. If I could go up to 25 feet, then instead of 10%, I could go a third. So I could have a 50 amp wire and have a short on that wire, and it would still open up that 150 amp breaker. So it's kind of crazy. They think that 15 amp wire can open up 150 amp breaker if you're only going 10 feet, or if you're only going 25 feet, a 50 amp wire could open up a 150 amp breaker. That's kind of like why we have those tap rules there. It's just because if it's going a short distance, there's not enough resistance to make the wire burn up before it opens up the breaker. So then when we're doing this with adding solar or energy storage, today's energy storage day, but it's the same thing for solar, instead of just taking that 150 amps, what we could do is we go 150 amps plus 125% of inverter current. So there's 32 amp inverter, that's an energy storage inverter today, times 1.25 is 40 amps, that's 125% of inverter current. And so then we end up with 190. And so there is 150 plus 40 is 190. And then we are going to multiply that times a third or divided by 3. And then we're going to get 63 amps. Make sure that conductor's at least 63 amps. Hey, it's at least 63 amps, so it's not a problem at all. That's kind of how that works.
And it always has a breaker at the end of the tap. So there's no overcurrent protective device at the start of the tap, but at the end of the tap, there's always an overcurrent device. This just says if it's at the end, you could call it a tap. And that's one nice way to talk about a PV system when we connect it in. If we connect it in toward the end or at the very end of a feeder, then the remaining section going to the sub panel could be called a tap. If it's at the opposite end, we're basically connecting in right at the bitter end of the feeder. There's no case where that 40 amp breaker, that 32 amps of PV, could hurt anything downstream of it because there's already a breaker there. There's already a main breaker in that 150 amp sub panel. And then all we're worried about is worst case scenario, could that PV system hurt us in our calculations for the tap that's happening on the 60 amp tap? And so what we did is we said, okay, we'll use the tap rule and we'll pretend like the PV system has the same fault current characteristics and capabilities as the utility. Now, does it? Of course not. We generalized Article 705 to all power sources, so you could have a power source like a synchronous generator or something like that, even though they're rare, that could be feeding current and fault current into that feeder. And then these tap rules would be preserved because they're still very conservative even for a generator. And so if it's a short tap, you're normally not going to have a problem. If it's a longer tap, it's just a little more than the rating of the circuit breaker. Now you would have to do the calculation of the ampacity of the tap, and normally the tap ampacity, if you have a 60 amp breaker on it, unless it was being upsized to the next breaker size, would be sufficient. So you do the calculation. If you came out with a 65 amp ampacity, great. If you came out with a 55 amp ampacity, that would not be great, and that conductor would have to be reconductored to the feeder.
Reconductored. Wow, that's no fun. Bus bars, they changed the numbering between 2017 and 2020 NEC, but not too much else was changed, but maybe a couple of subtle things. And so we've got B31 now. What was that? It was B3A, I think, before. And not exceeding the bus bar ampacity. I call that the 100% rule or option before. In our last book, we started changing them to the 120% option instead of rule because people were getting confused and thinking you always had to do this because you don't. B32 is the 120% option. And then B33, the solar plus the load break method. And I was calling it the sum rule, and you call it?
Some of the branch circuit breakers.
Some of the branch circuit breakers.
Protecting the panel. So you protect the panel with the sum of the branch circuit breakers rather than a main breaker.
And then we have the center fed 120% rule. Now you could go from both sides, which you could before. There's a TIA, an amendment that happened in 2016 or something like that. Engineering supervision, the most underutilized great way of doing things. And then also we sometimes have feed-through conductors, which is just like at the end of your bus bar.
And that was added in the 2020 code. That's not in the 2017.
Yep. And so at the end of your bus bar at the bottom, you might have some couple of terminals to screw on some feed-through conductors. So it's like, I always like to look at that as it's just like a big extension of your bus bar. So the difference between the 120% rule, which I bet all of you are familiar with, and the 100% rule is pretty much if you're not exceeding the bus bar at all, when you add up 125% of the inverter current to the main breaker, if you're not exceeding that at all, you don't have to put them at the opposite end of the bus bar. Like, at the bottom side of the bus bar, you can stick it anywhere that you want. And also, too, there was a change, I think that was in the 2014 NEC where they first brought it in. In the 2011 NEC and before, we did it based on the size of the inverter breaker. And now it's based on 125% of the inverter current. So let's say you had like one in-phase inverter on a 20 amp breaker. You don't have to use 20 amps there. You would use just like closer to 1 amp in your calculation. And then the 120% rule, which probably everybody's familiar with because it's everybody's favorite thing in the NEC is the 120% rule. The main breaker, the bus bar, and so if there's a 100 amp bus bar and a 100 amp main breaker, bus bar times 1.2, 120% is 120 amps. Subtract off a 100 amp bus bar, that leaves us with 20 amps. So that would be 125% of inverter current would be 20 amps. So that means we could take 20 times 0.8 or divided by 1.25 equals 16 amps. So we could have a 16 amp inverter because 16 times 1.25 is 20. And that would be the most that we could do. A nice, easy way to install things, just popping in a breaker, not having to work with dangerous conductors on the supply side of the main breaker. And then the other thing that you need to do is to have this label telling people not to relocate that breaker. It's got to be at the opposite end of the bus bar. And then the other thing that you can do that sometimes people are confused about is if we've got a 200 amp bus bar and a 200 amp main breaker, that gives us 40 amps. And we don't have to put it all on one breaker. We can put it on two different breakers at the opposite end of the bus bar. So we could have two separate 20 amp breakers.
They're actually connecting into the very same tabs. So essentially when we say opposite end, that's as far as you can go. And so some people will try to get real technical about, is that truly the opposite end? Well, both those tabs are the opposite end. You could split it up to two different breakers. And why would we do that? Well, common reason would be for things like microinverters and things like that, where the microinverter requires no greater than a 20 amp circuit breaker. So we have two microinverter circuits coming into our panel, we could do it this way. And in fact, you could do 4 because all 4 of those would still be at the opposite end. Again, what we're trying to capture is that all the loads are in between the sources and the main breaker. And so as long as we don't intermix any loads in there at the bottom of the panel, then there's no chance of that section of the panel ever getting overcurrent. And that's really what we're down to. Now with microinverters, as most of you guys are very familiar with, the N-phase microinverter, a lot of people use their little combiner panel, and that's a really handy unit because it's got the communications built into it and stuff like that. So a lot of people use that. So you don't see this kind of thing being done a lot with N-phase anymore just because it's common to be using those other tools that are from the manufacturer.
I think like some people get confused when they read the NEC and they think that it says that it all has to be only one breaker.
Yeah. Each connection of source has to be on a breaker, but you can have multiple source connections.
The sum rules, so we just go 20, 40, 60, 80, 100. We don't even have to look to see if it's solar or load breakers. And we don't really have to pay attention to like the main breaker. I even think that why even have a main breaker? Because we're protecting everything in reverse. If you have 100 amps of breakers, there's never going to be more than 100 amps coming out of there. Doesn't have to be at any certain side of the bus bar or anything like that. But one thing, Bill, that I think that this maybe could be changed a little bit in the future is single pole breakers. Have you seen anybody like try to deal with that? Like two single pole breakers would be the same as one 2-pole breaker.
Right. It's the same issue you would have with 3-phase systems. It's the same exact issue. 2 single pole breakers on opposite sides of the bus are completely separate. So each bus bar, if you think about it, this is a 2-bus system and 3-phase system is a 3-bus system. And so you are looking at summing the currents on each bus. That can be confusing to some folks. There's no reason that if you had 2 20-amp breakers and they were on opposite buses, you're not going to count them twice.
Yeah. I mean, if you read the wording, though, it makes it sound like you're going to count it twice. And maybe it's just so people don't mess up and then somebody would try to relocate it. And,
I mean, a lot of this is trying to make it as simple as you possibly can. Now, there's nothing to prevent you from using a 2-pole breaker on a single pole circuit. For instance, we do that already with multi-wire branch circuits. So we put a 2-pole breaker on a multi-wire branch circuit. And so that would be another way so that you could have as many circuits as you could. You just use all 2-pole breakers in a panel like this. That's often the way it goes because you're just trying to make sure that nobody overcurrents this panel by putting too much load and power source at the same time. And it's a huge benefit. I mean, being able to do this, it took us several code cycles to figure out what would work in a very simplistic manner that anybody could kind of connect with. And so this idea of you got a 100 amp panel or 200 amp panel, all you have to do is just total the load breakers and you're good to go. I would say for a split phase panel, the easy way to fix that is to use all 2-pole breakers, and then if you have single pole loads that you're pulling off of it, then you can do 2 single pole off of the same breaker.
Okay, that kind of makes sense. So like, what do you think? If somebody had 2 single pole breakers that were 20 amps instead of one of these, would you fail them or would you let them do it?
Well, personally, I probably wouldn't fail them.
Unless they were a jerk?
Yeah, unless they were a jerk. It might be a good way for AHJs to express it to the clients or to the contractors that are out there. If you use the 2-pole breaker, then you never get in trouble with this, as you're pointing out. This was intended to be, you count on your fingers and your toes, and if you can use your fingers and toes to figure it out, then you're probably good to go. It was intended to do it without a lot of calculation, and that's why it's so simplistically written.
Change to the 2020 NEC. It has to do with center-fed bus bars at the 120% rule. So sometimes you'll get a bus bar that's fed from the middle, so the main breaker's in the middle of the bus bar, and at first we couldn't do the 120% rule at all. Then we could do the 120% rule, but it would just have to be on one side or the other, not both. And now the 2020 NEC, we can put things on both sides. And so...
Yeah, and the point here was that this language was actually drafted in cooperation. I put it together with Fred Hartwell, who's been working with the code for years and years and years, and I didn't want to mess with his wording. The intention was that you can't count twice. That's the key, is that if you had a 200 amp panel like you have here, you couldn't put a 40 at each end. But there's nothing wrong with putting two 20s for the total of the 120% rule. And so that's why everybody got the message that we're not trying to make it so that you could do the 120% rule on the top half of the bus and again on the bottom half of the bus. But there's nothing wrong with splitting the current so that you have one end phase 20 amp circuit on the top of your panel board and another 20 amp going to SMA inverter at the bottom.
Great. To me, it makes more sense to have it both on opposite sides.
And you may not have room. Quite frankly, a lot of these split panels, and I don't know how many they have in Hawaii, quite frankly. They're very common in California and Arizona and hot climates. But where you have a situation where the bottom half of the panel tends to be the larger two-pole breaker spaces, and there's less of them, whereas there's more single-pole spaces available on the upper part of the panel. You would tend to put it at the top of the panel because that's where there are typically more breaker spaces available. But you also may have an extra space at the bottom and only, two extra spaces at the top. So that's why splitting them up may just be simpler so you don't have to go rewire your entire distribution panel.
Multi-ampacity bus bars. So this is the one where it says we can do things under engineering supervision. This is a good thing that could be used a lot. And you could even do the 200% rule here, So
absolutely. There's a lot of cases, especially in commercial switchgear and all, where there's just no chance of overcurrent anything. And an engineer can look at that, do the calculations, provide a little letter showing the calculations, and AHJs should freely accept that. I've done it several times in installations. Those installations are running great, nothing wrong with them. And having to change out panel boards and switchgear and stuff can be exceedingly expensive. And just a simple calculation and placement shows these things to be fine. And anytime we've got switchgear and things like that, when we're adding loads to it in the first place, the switchgear was designed and built for the building to start with. And any additions are going to have to go through an engineer. This is just saying, hey, if we're already going through an engineer to add a source or a load, show the calculations and show that everything's fine. So there's no 120% rule on switchgear or anything like that. It's just whatever the calculations come out to be, as long as it doesn't overcurrent the equipment, you're good to go.
Good to go. All right. The last one here is the feed-through lugs.
And that's new again in the 2020 code. So if you have feed-through lugs, or feed-through conductors is the correct term. We often call them feed-through lugs at the bottom of a bus bar, and those are the lugs that we attach feed-through conductors to that go to an additional sub-panel that are all being protected by the main breaker. That main breaker might be a 100 amp main breaker, or it could be a 200 amp main breaker. And so this shows what the details are, is that if we put an overcurrent device coming off of that feed-through lugs, we can now use the 120% rule in the first panel, and we could also use the 120% rule downstream and then run it back up to the main panel. So it's just providing some additional information on this idea, and I think Sean explained it really well, that it's an extension of the bus bar. And so we could put all the solar at the bottom of that bus bar, or if we put an overcurrent device, we can put solar at the bottom of that first bus bar, because the next feeder section has been protected in a similar way that we were protecting feeders previously, where we'd interject solar like the Hawaiian tie-in, where we tie in solar in the middle of a feeder and then put an overcurrent device on the load side of that connection point, and that protects everything downstream.
The fun one, 705.13. And so this is where you can just add all kinds of stuff and use brains. So they call this PCS, or power control system. So you can just pretty much use CTs is what people are using to control the power output. One way of thinking of this is like, how often is somebody going to be blasting out all the power from their battery and all the power for their PV system at the same time? Probably never, because you're going to be charging your battery with your PV system instead of discharging your battery. Why not control all that stuff, and then you don't have to size everything based on the currents coming out of both at once, when you're never going to be putting them both out at once at the same time, because you can control it with electronics.
Yeah, and there is a standard now. We call it a CRD that's in addition to UL 1741. So there are several products on the market that have been certified for power control systems, including the Tesla Powerwall, the newer versions of the Tesla Powerwall. Enphase has a power control system, and I believe SolarEdge does as well. It allows you to bring together a lot more power than the 120% rule would allow you to do and other things would allow you to do. And you're controlling all these things rather than relying on just simple calculations. And some of those calculations aren't so simple that we just prove as we walk through all those things. But this is really the way of the future. It's the way of basically bringing together lots of solar, lots of energy storage, maybe even a car, vehicle to grid, we talked about earlier, and summing them all into a same panel. They could all go into the same electrical panel, and it could be a 200 amp rated panel, something like that. We could have 400 amps of power coming into it, and all this is being controlled through control logic that's going through a listing process, controlling the brains of these computers. And guess what? You know how we got this idea? We got it from Article 625, which is going back to the sequencer that's allowed to sequence the power to all those chargers with a much smaller feeder than having to size the feeder for the full load with all cars parked in and charging at full power. That's the concept. We're working with that concept. The concept is well understood in the electric vehicle charging world, and the concept works very similarly and effectively when we've got solar and energy storage in the same way.
In a way, this is sort of like what they're doing in Hawaii, where they're not allowed to export to the grid, so they put a CT around the service entrance conductors. That's kind of like a power control system right there.
It is a power control system. In fact, those things are now being certified through that process. So Hawaii also, really blazed the way for that whole concept. And the good news is the utilities have accepted that, and it's worked very well. In the future, we'll have things that are not just zero net export. As I pointed out before, we'd have where the export is set at 5 kilowatts or 10 kilowatts or whatever the utility will allow.
We got one question. Right. Was there anything in the code about physical protection of a power wall, for example, in a garage like a ballard or a curve stop? We actually just recorded some stuff on that.
Yes, we did. And the answer is that's in the residential code. The residential code requires vehicle impact protection if the energy storage system is in a location where a vehicle could hit it easily. The ICC has provided some additional information on vehicle impact protection for things like furnaces and water heaters and stuff like that. And basically what they've said is that if it's on the end wall of the garage where the car is pulling in, then it needs some kind of protection. If it's on the sidewall, it doesn't need protection. That's a simple thing to work off of. And that protection could be in the form of parking wheel stop, or it could be in the form of a bollard. Wheel stops are generally easier to install and can be just as effective. Bollards tend to be a little more difficult to install. It really depends on the foundation and the slab that the garage has or the driveway. This could be for a driveway outside of a house where somebody could pull their car right up to it. So if you pave right up to where a battery is, then you'd probably need some kind of vehicle impact protection like a wheel stop or a bollard.
Yeah, we got one more. Can PCS be used to stop people from overloading a panel? Maybe with smart devices or just controlling the power producing circuits?
Power control systems are for the power supply side of the equation. Energy management or load management is for the load side, for overloading the panel. So yes, to answer your question, power control systems would prevent from overloading the panel from a supply point of view, and the load management system would prevent the load from being too high to overload the panel. So where we're going to see this go in the future is that the power control system and energy management, it'll be a total energy management system which will do power control and load control, and the two working together, knowing what they're doing, will keep the overall panel load controlled, and these will be called smart panels, if you will. Smart load centers that can do both the load and power source side of the equation.
Thanks for listening to Sean White's Solar and Energy Storage Podcast. By the way, if you wanted to get some visuals that might go along with this presentation, You can get our book, PV in the NEC. Any version will do, but the latest version is the 3rd edition. However, most people are not on the 2023 National Electrical Code. Most people in this country are on the 2020 National Electrical Code. But if you want some visuals also, you can go to SolarSean, that's solarsean.com, and look for the PDF download tab and check out the NEC presentation that we have there. Also, if you want to see Bill's website, that's at brooksolar.com with 1 S. And if you want to get some NABCEP certification continuing education credits, or you want to qualify for a NABCEP exam, check out heatspring.com/Sean, or it's easier to just go to SolarSean, that's solarsean.com, and then you can click the HeatSpring link from there. SolarSean.com.